Hello everyone. Welcome to this fantastic journey through the world of machine learning. In this video, we will explore random forest, a powerful ensemble learning algorithm that combines the predictions of multiple decision trees to make more accurate predictions. We will delve into the functioning of random forest, advantages and disadvantages, and explore its derivatives. In the video description, you'll find links to related videos and playlists on today's topic. I invite you to take a look because there is further information or insights that could interest you. If you'll find in this video concepts or topics that you didn't fully grasp, you can look in the description for additional explanations and helpful resources. I understand that some ideas or concepts might seem complex, but I'm here to simplify and make these topics accessible. If you don't understand something, please ask in the comments. Before we begin, I'd like to ask, if you haven't already, to subscribe to my channel. Random forest is a widely used algorithm based on boosting, an ensemble learning technique that combines the predictions of multiple decision trees to make more accurate predictions. It is known for its versatility and effectiveness in various domains, including classification and regression tasks. The algorithm derives its name from the fact that it creates a forest of decision trees, where each tree is trained on a random subset of the available data and a random subset of features, which helps to reduce the correlation among the trees. During prediction, the final output is determined by aggregating the predictions of all the individual trees through voting, for classification, or averaging, for regression. Let's follow a step-by-step breakdown of the functioning of the random forest algorithm. Initialize the number of trees in the forest and the number of features to consider at each split. Randomly select a subset of the training data called the bootstrap sample. The selection is done with replacement, meaning that each data item can be chosen multiple times, allowing for potential duplicates in the subsets. Randomly select a chosen number of features. Create a decision tree using the bootstrap sample and the selected features. At each node, select the best split among the features and split the node based on its optimal threshold. Repeat the splitting process recursively until a stopping criterion is met, like maximum tree depth or minimum number of samples per leaf. Repeat the process for the chosen number of trees. Note that these steps represent a general overview of the random forest algorithm. The exact implementation may vary depending on the specific framework or library used. Additionally, there may be other optimizations or variations that can be applied to improve the algorithm's performance or address specific requirements of the problem at hand. Here's the process to get a prediction from new data. Pass the data through each decision tree in the forest. Obtain the prediction from each tree. For classification, a class label. For regression, a numeric value. Aggregate the predictions by voting for classification or by averaging for regression. Random forests offer several advantages that contribute to their popularity in machine learning. High accuracy. Random forests are known for their ability to deliver high predictive accuracy, often outperforming single decision trees in many other machine learning algorithms. Handling high-dimensional datasets. A key characteristic of a random forest is its ability to handle high-dimensional datasets with a large number of features. As the algorithm operates with a random subset of features for each individual decision tree, it reduces the likelihood of selecting the same features between the different trees. Reduced variance. Additionally, due to the random selection of samples derived from the bootstrap method, each trained decision tree is exposed to distinct subsets of the data, capturing different aspects of the underlying relationships. This creates trees that are specialized on the various features, contributing to generalization with new, unseen data, as an ensemble of models. This approach effectively decreases the typical variance of decision trees. You can explore this aspect in the decision tree video. Resistance to overfitting. Overfitting occurs when a machine learning model becomes overly specialized in capturing the unique characteristics, irregularities, and noise present in the training data, which ultimately leads to poor performance on new, unseen data. Thanks to their built-in mechanism of randomness, random forests are also resistant to overfitting. Feature importance. The algorithm provides a measure of feature importance, indicating which features have the most impact on the predictions. The importance of each feature is typically expressed as decimal numbers ranging from 0 to 1. This information can aid in feature selection and understanding the underlying problem. Robustness to outliers. Random forests are less affected by outliers compared to other algorithms, thanks to their averaging or voting mechanism. Versatility. Random forests can handle various types of data, including categorical and numerical features. They can be applied to both classification and regression problems. However, random forests also have some limitations to consider. Interpretability. While random forests provide feature importance, the overall model interpretation can be challenging due to the complexity of the ensemble of trees. It can be difficult to understand the exact relationships between features and predictions. Computational complexity. Training a random forest can be computationally expensive, especially for large datasets with many trees. The time and resource requirements may increase as the number of features and training instances grow. Random forests can consume significant memory resources, especially if the trees are deep or if there are many features. Random forests have several derivatives that are tailored for specific tasks or address certain limitations. Here are a few notable ones. Extra trees. This variant of random forests further increases the randomness by randomly selecting splitting thresholds instead of searching for the best one. It trades off some accuracy for faster training and prediction times. Extremely randomized trees. Similar to extra trees, this variant adds an additional layer of randomness by randomly selecting a subset of features at each split, without considering any optimal thresholds. This approach can reduce the variance and increase the diversity of the trees. Random multi-model deep learning forests. This derivative combines random forests with deep learning techniques. It aims to improve the performance by integrating the strength of both approaches, leveraging the ability to capture complex data patterns of deep neural networks and the interpretability of random forests. In summary, random forests are a powerful ensemble learning algorithm that combines the predictions of multiple decision trees by randomly selecting data subsets and features to make more accurate predictions. Random forests offer high accuracy, handling high-dimensional datasets, reduced variance, resistance to overfitting, feature importance measurement, robustness to outliers, and versatility, but they also come with challenges related to interpretation and computational complexity. They have various derivatives, like extra trees, extremely randomized trees, and random multi-model deep learning forests. Here's a recap of the algorithm. If you want, you can remix this part with your mobile phone. Initialize the number of trees in the forest and the number of features to consider at each split. Randomly select a subset of the training data called the bootstrap sample. The selection is done with replacement, meaning that each data item can be chosen multiple times, allowing for potential duplicates in the subsets. Randomly select a chosen number of features. Create a decision tree using the bootstrap sample and the selected features. At each node, select the best split among the features and split the node based on its optimal threshold. Repeat the splitting process recursively until a stopping criterion is met, like maximum tree depth or minimum number of samples per leaf. Repeat the process for the chosen number of trees.
And that brings us to the end of today's video. Thank you so much for watching and being a part of this journey. I truly appreciate your support. Don't hesitate to engage with me through the comments. I love hearing your thoughts, questions, and suggestions. Your input helps me tailor my content to your needs and interests. Leaving a like, sharing the videos, or commenting can make a huge difference. If you haven't already, please consider subscribing to my channel. It's a simple gesture, but it means the world to me. There's a lot of effort behind each video. I put in all my dedication to try and create interesting and to-the-point content. If you click on the subscribe button, I can go on creating for you free and quality service. Thank you once again for being here, and I look forward to seeing you in the next video.